For years, one sentence was repeated so often that it became accepted as fact. Without ASML's most advanced EUV machines, China cannot produce cutting-edge chips. It sounded reasonable. It was backed by export controls, engineering textbooks, and some of the smartest semiconductor experts on Earth. Then something uncomfortable happened. China didn't receive the machines. Yet, advanced chips kept appearing, not in the quantities that Taiwan or South Korea could produce. Not with the same efficiency either, but they existed, they worked, and they forced people to ask a question that was never supposed to matter. How do you build something you're supposedly locked out of building? That question reaches far beyond smartphones. Every artificial intelligence model, every military drone, every satellite, every modern data center, and almost every piece of advanced manufacturing depends on increasingly powerful semiconductor chips. Whoever controls the ability to manufacture them doesn't just dominate technology. They influence economics, national security, and the speed of innovation itself. That's why the United States tightened export controls in October 2022. The restrictions weren't aimed at slowing one company. They targeted an entire technological ecosystem. ASML in the Netherlands could no longer ship its most advanced EUV lithography systems to China. American companies faced new licensing requirements. Japan joined restrictions on several critical manufacturing tools. The expectation was straightforward. No EUV, no advanced chips. Case closed. Except engineering has a habit of ignoring political expectations. One of the biggest mistakes people make is assuming semiconductor progress follows only one path. It doesn't. The industry often celebrates the newest machine while overlooking the thousands of smaller improvements surrounding it. Sometimes those overlooked improvements become the real story. That's exactly where China's engineers focused. Instead of asking, how do we obtain ASML's EUV machine, they asked a far stranger question. What if we don't actually need it? Those two questions sound almost identical. They're not. One accepts the existing rules, the other changes the game. This is where companies like SMIC entered the picture. China's largest semiconductor foundry wasn't expected to compete with industry leaders at the most advanced nodes. Even optimistic analysts believed the gap was simply too large. Building chips below 10 nanometers without EUV lithography was considered painfully inefficient, commercially impractical, and according to several veteran chip engineers, close to impossible. Notice that word, impossible. Engineers rarely use it lightly. In semiconductor manufacturing, shrinking features by just a few nanometers means dealing with errors measured in billionths of a meter. Imagine trying to paint microscopic highways narrower than viruses while ensuring billions of transistors connect perfectly across an entire silicon wafer. That's the level of precision involved. Then China attempted something most competitors had already abandoned. It pushed older deep ultraviolet lithography, DUV, far beyond the limits it was originally designed for. Think of it like climbing Mount Everest, wearing equipment meant for a much smaller mountain. You wouldn't recommend it. You certainly wouldn't expect someone to reach the summit. Yet, if they somehow did, you'd stop laughing and start asking how. That how is the real story. Because this wasn't one invention or one miracle breakthrough. It was dozens of engineering compromises, software advances, manufacturing tricks, and extraordinary process discipline stacked on top of one another until the impossible slowly became nearly expensive. And expensive can be solved, impossible cannot. My view is that many discussions about China's semiconductor industry have focused too much on what it lacks and too little on how engineers respond when options disappear. History suggests constraints often produce unusual innovation, although not always elegant innovation. The question isn't whether China's approach is as efficient as ASML's ecosystem. It isn't. The more interesting question is whether efficiency was ever the objective in the first place. To understand what China actually accomplished, you have to forget the marketing language that dominates the semiconductor industry. People love to compare chip manufacturing to a race. It isn't. It's closer to solving an impossible puzzle where every missing piece forces you to redesign the picture itself. The machine everyone talks about, ASML's extreme ultraviolet lithography system, is extraordinary because it simplifies manufacturing at the most advanced nodes. Instead of exposing intricate transistor patterns over and over again, EUV dramatically reduces the number of processing steps required. Fewer steps mean fewer chances for microscopic errors. better yields, lower costs, faster production. China didn't have that luxury, so it leaned on a technique called multiple patterning. Imagine drawing one perfect circle. Easy. Now imagine drawing the exact same circle 5 separate times, each perfectly aligned with the last, using increasingly thinner pens. If your hand slips by even a fraction of a millimeter, the final image is ruined. Shrink that mistake down to the atomic scale. That's semiconductor manufacturing without EUV. Each additional exposure increases complexity. Every alignment has to be almost flawless. Every wafer spends more time inside the factory. Every extra processing step creates another opportunity for defects that can destroy billions of transistors in an instant. Critics looked at those economics and concluded the same thing. No company would willingly manufacture chips this way. From a purely commercial perspective, they had a point. But commercial logic isn't always national strategy. When the objective changes from maximizing quarterly profits to ensuring technological independence, the calculation changes with it. A chip that costs more to manufacture is still infinitely more valuable than a chip you cannot produce at all. That distinction explains decisions that puzzled many observers. SMIC wasn't simply buying equipment, it was redesigning manufacturing flows around the equipment already available. Engineers refined photoresists. They improved overlay accuracy. Process control software became more sophisticated. Defect inspection tightened. Chemical polishing became more precise. Each improvement looked small in isolation. Together, they created something larger. This is one of those moments where semiconductor history repeats itself. Intel faced similar manufacturing walls decades ago. So did TSMC. Every major chipmaker has encountered physical limits that experts believed would halt progress. The difference was that those companies usually solved the problem with better tools arriving at roughly the right time. China faced the same wall after someone locked the toolbox. That doesn't guarantee success. It simply changes the nature of the engineering challenge. The best example arrived in 2023, when Huawei introduced the Mate 60 Pro, powered by the Kirin 9000S processor. Overnight, analysts around the world began taking the device apart. Governments paid attention. Semiconductor researchers examined die photographs. Reverse engineers measured transistor layouts. The conclusion surprised almost everyone. The processor appeared to have been manufactured using SMIC's approximately 7-nanometer class process without access to EUV lithography. Notice what happened next. The debate shifted almost immediately. People stopped asking whether China could manufacture advanced chips. They started arguing about how many it could manufacture. That's an entirely different conversation. Volume matters because semiconductor manufacturing is ultimately an economics game. Producing 10,000 advanced chips proves technical capability. Producing 10 million proves industrial capability. Producing hundreds of millions changes global markets. China hasn't reached that final stage. Not yet. Yield rates remain a major question. Manufacturing costs are almost certainly higher than competitors using EUV. Production speed is slower. These limitations are real, and ignoring them would distort the picture. At the same time, dismissing the achievement because it isn't perfect misses the larger point. My view is that too many discussions confuse less efficient with not viable. Those are different judgments. History is full of technologies that began as expensive, awkward, and inefficient, before years of relentless refinement transformed them into industry standards. There's another reason this matters. If engineers can stretch yesterday's tools much further than experts predicted, then assumptions about tomorrow's technological limits deserve another look. Because the next chapter isn't about what China built with older machines. It's about what happens when those engineers begin building machines of their own. There's a temptation to treat this as a story about one processor, one company, or one surprising product launch. I think that's too small. The real shift isn't happening inside Huawei. It's happening inside China's entire semiconductor ecosystem, where each success removes pressure from the next problem. That's how industrial revolutions usually unfold, not through a single invention, but through thousands of improvements feeding each other. Remember the question from the beginning? Why didn't China spend all of its energy trying to copy ASML? Because ASML's machine is only the visible tip of an enormous industrial iceberg. An EUV lithography system contains well over 100,000 individual components. It relies on mirrors polished by Germany's Zeiss, with imperfections measured in fractions of a nanometer. The laser system comes from the American company Cymer. Precision stages, vacuum systems, optics, specialty chemicals, software, and metrology equipment are sourced from suppliers across Europe, Japan, and the United States. You don't replace that overnight. You build around it while slowly replacing pieces of it. That's exactly what China has been attempting. Shanghai Microelectronics Equipment, better known as SMEE, has spent years developing domestic lithography machines. Chinese companies have expanded production of semiconductor chemicals, silicon wafers, photoresists, etching tools, deposition equipment, and inspection systems. None of these headlines generate millions of views, yet together they form the industrial foundation that advanced chip manufacturing actually depends on. It's a little like building an airline. People admire the airplane. They rarely think about airports, radar systems, maintenance crews, fuel pipelines, or pilot training. Without those, the airplane never leaves the ground. Semiconductors work the same way. This is where I think many forecasts underestimated China's response. The assumption was that export controls would permanently freeze technological progress. Instead, they accelerated domestic investment. Beijing expanded funding through the National Integrated Circuit Industry Investment Fund, often called the Big Fund, while provincial governments poured billions more into semiconductor research, manufacturing, and equipment suppliers. Does that mean every investment succeeded? Not even close. Several projects failed spectacularly. Some local governments financed factories that never reached commercial production. Others suffered from poor management, corruption, or unrealistic expectations. Throwing money at engineering problems doesn't automatically create breakthroughs. That's the strongest argument made by skeptics, and it's a fair one. But here's where the picture changes. Even if half the projects fail, the surviving half creates engineers, suppliers, manufacturing knowledge, and production experience that didn't exist before. Industrial capability compounds over time. Failures don't always erase progress. Sometimes they become expensive lessons that shorten the next learning curve. That brings us to the reversal in this story. Many people believe the biggest risk for companies like Intel, Samsung, or TSMC is that China eventually catches up in pure technology. I disagree. The more immediate challenge is something else. What if China becomes good enough? History shows that markets don't always reward whoever builds the absolute best product. They often reward whoever builds a product that's reliable, available, and affordable at massive scale. Think about electric vehicles. For years, critics argued Chinese manufacturers couldn't match established global brands. Then, companies like BYD shifted the conversation. They didn't need to dominate every category. They simply had to become competitive enough while producing millions of vehicles. The market responded. Semiconductors could follow a similar path, not because China's chips are superior today. They aren't across many leading-edge applications, but because good enough, combined with enormous manufacturing capacity, can reshape industries surprisingly quickly. My prediction is that the next phase won't be decided by one dramatic technological breakthrough. It will be decided by something far less exciting. Thousands of engineers improving yields by 1% here, reducing defects by 2% there, shortening production time by a few hours, replacing another imported component with a domestic one. Those incremental gains rarely make headlines, but over 5 or 10 years, they can completely rewrite the competitive landscape. And that leads to the final question. If sanctions unintentionally accelerated China's determination to build an independent semiconductor ecosystem, what happens when that ecosystem no longer depends on catching up, but starts setting its own direction? The semiconductor story didn't begin with a chip. It began with a dependency. For nearly 3 decades, the industry became so specialized that no single country could build a leading-edge processor entirely on its own. One nation produced the software, another mastered the optics, a different one supplied the lasers. Taiwan perfected manufacturing. Japan dominated specialty materials. The Netherlands built the world's most sophisticated lithography machines. It wasn't just globalization, it was extreme specialization. That system was incredibly efficient, right up until geopolitics entered the clean room. Once technology became a strategic asset rather than simply a commercial one, governments started treating semiconductor supply chains the way they once treated oil fields and naval routes. Efficiency became secondary. Resilience became the priority. China adapted to that reality faster than many expected. To be clear, this doesn't mean China has overtaken ASML. It hasn't. It doesn't mean SMIC has surpassed TSMC. It hasn't. And it certainly doesn't mean export controls failed completely. They have slowed China's progress at the leading edge and increased the cost of getting there. But slowing someone down and stopping them are two very different outcomes. That's the distinction history may remember. If you look back at previous industrial revolutions, countries rarely abandoned an objective simply because it became more difficult. They changed timelines, they changed methods, they accepted higher costs. Eventually, some of those investments paid off. China appears to be following that same pattern. The interesting part is what happens outside China. The United States has responded with the CHIPS and Science Act, encouraging domestic manufacturing while strengthening partnerships with allies like Japan, South Korea, and the Netherlands. Europe is investing heavily in semiconductor production of its own. India is trying to establish itself as a new manufacturing destination. Even countries that never considered chips a national security issue 5 years ago are building semiconductor strategies. In other words, this isn't becoming a race between China and America. It's becoming a race to build the most resilient industrial ecosystem. Those are not the same competition, and resilience is much harder to measure than transistor density. Here's another thought that often gets overlooked. Competition usually creates better technology. When one company dominates a market for too long, innovation tends to become incremental. When multiple serious competitors emerge, engineering accelerates because nobody can afford complacency. Ironically, the attempt to preserve technological leadership may end up producing more global innovation, not less. Of course, there are risks. A fragmented semiconductor industry could become more expensive. Duplicate supply chains increase costs. Companies may need to design different products for different markets. Research collaboration could become more difficult. Consumers may eventually pay higher prices for everything from smartphones to electric vehicles. That's the bill that comes with technological fragmentation. Whether it's worth paying is ultimately a political decision, not an engineering one. If I had to make one prediction, it's this. The next decade won't be defined by a single breakthrough that suddenly changes the balance of power. Instead, we'll wake up one morning and realize that what once seemed impossible has quietly become ordinary. That's usually how industrial history works. People remember dramatic announcements. Factories remember steady progress. So when someone says, China built a chip without ASML, I think they're asking the wrong question. The better question is, why so many intelligent people believe there was only one path forward in the first place. Engineering has a habit of finding another route. Sometimes it's slower, sometimes it's more expensive, sometimes it looks inefficient until one day it doesn't. And that's why this story isn't really about one chip. It's about what happens when a country decides that dependence is no longer an acceptable strategy, and then spends years proving that determination can be an engineering resource of its own. If you enjoyed this deep dive and want more stories where technology, economics, and geopolitics collide beneath the headlines, consider subscribing. There are plenty more assumptions worth testing.